Hey everyone! Last episode we learned how logistic regression can classify between two classes and how the sigmoid function can turn any score into a probability between 0 and 1. This is worth a quick recap because everything we're about to do in this episode builds directly on from it. And if any of this feels unfamiliar, I'll definitely recommend watching episode 2 first. At its core, logistic regression is really just an extension of linear regression. We take our dataset, multiply it by the parameter vectors theta, and produce a score. The problem with this is that the score can be any real number, but probabilities need to be between 0 and 1. And that's exactly why we introduced the sigmoid function. We also discovered that mean squared error isn't the right loss function for logistic regression. It doesn't penalize confident mistakes strongly enough. And more importantly, it creates a non-convex optimization problem. So if the mean squared error doesn't work, what loss function does? By the end of this video, I don't want us to just know the answer. I want us to discover why it works, as if we were inventing it ourselves. So to answer the question of what our loss function should look like, I think it's worth reminding ourselves what we're actually trying to do. The goal is to find the parameters theta that make the data we've observed as likely as possible, according to our model. Here's what I mean. Suppose our model predicts 0.99. In other words, based on everything it has learned, it believes that there's a 99% chance that this cell is malignant. Now, let's say the actual label is 1, the cell really is malignant. So, according to our model, the probability of observing what actually happened is 0.99. Now, imagine a different scenario. Our model predicts 0.01, but the actual label is still 1. The cell is still malignant, but this time, according to our model, the probability of observing what actually happened is just 1%. So, naturally, we'd prefer the first model over the second. Now, some of you might be wondering, well, if bigger probabilities are always better, can't we just make P as large as possible? It sounds reasonable, but we've only looked at cells that are actually malignant. What happens when the cell is actually benign? Suppose our model predicts 0.09 again. It's saying there's a 99% chance the cell is malignant, which means that there's a 1% chance the cell is benign. Now, suppose the actual label is 0, the cell really is benign. So, according to our model, the probability of observing what actually happened isn't P anymore, is it? It's 1 minus P. And that's the key idea. Sometimes the probability we want is P, and sometimes it's 1 minus P. It all depends on what the true label actually is. So now we're starting to build a formula. From the last scene, we know that the probability of observing the correct label depends on two possible values, P and 1 minus P. But our formula can't only depend on the prediction, it also needs to depend on reality. For example, y can be one of two values, 0 and 1. So the question is, can we build one formula that automatically chooses P when y is equal to 1 and automatically chooses 1 minus P when y is equal to 0? The easiest way to think about this is like a pair of light switches. When y is 1, we want the P switch to turn on, and we want the 1 minus P switch to turn off. When y is equal to 0, we want the opposite. We want P to turn off and 1 minus P to turn on. So how do we turn part of a formula off? We make it equal to 1. Because multiplying by 1 doesn't change anything. For example, x times 1 is always equal to x. And how do we make something equal to 1? We raise it to the power of 0. Because anything to the power of 0 is 1. So let's look at P. If we raise P to the power of y, then two things can happen. If y is equal to 1, P to the power of y will just be P. And so P just stays on. But if y is equal to 0, P to the power of y will just be 1. So P turns off. Now, what about 1 minus P? Should we also raise that to the power of y? Not quite. Because 1 minus P needs to turn on when y is equal to 0, not when y is equal to 1. So instead, we raise it to the power of 1 minus y. So if y is equal to 0, 1 minus P to the power of 1 minus y will just be 1 minus P. So 1 minus P turns on. And if y is equal to 1, 1 minus p to the power of 1 minus y will just be 1. So 1 minus p turns off. Now we can combine both switches into one formula. P to the power of y multiplied by 1 minus p to the power of 1 minus y. And this is beautiful, because when the true label is 1, the formula becomes p. And when the true label is 0, the formula becomes 1 minus p. And that's exactly what we wanted. Remember our original goal. We wanted to find the parameters theta that makes the data we've observed as likely as possible. Well, this formula tells us exactly how likely one training example is. But there's one problem. Our dataset doesn't contain just one example. It might contain hundreds, thousands, or even millions. So how do we measure how likely our entire dataset is? Well, if each training example is independent, the probability of observing all of them is simply the product of every one of these terms. The probability of seeing the entire dataset given our parameters is the product of all individual data points. So where L of theta means the probability of seeing this dataset if our parameters were those values of theta. But there's a problem, a surprisingly sneaky one. Every one of these probabilities lies between 0 and 1. And when you keep multiplying numbers smaller than 1 together, the results become incredibly small. Even if your model is making excellent predictions, it makes likelihood harder to work with. Fortunately, mathematics gives us a really elegant solution. Instead of working with the likelihood directly, we take the logarithm. Now, some of you might be wondering, why the logarithm? Because logarithms have a beautiful property. The logarithm of a product is equal to the sum of the logarithm. And if you want to differentiate that, it's much easier to differentiate sums than products, because the derivative of a sum is basically the sum of the derivatives. So let's apply that to our likelihood. We start with the logarithm of the product. Using the logarithm rule, we can move the logarithm inside and turn the product into a sum. Now, remember what each individual likelihood was. It was p to the power of y multiplied by 1 minus p to the power of 1 minus y. So we simply substitute that into every term, and there's one final logarithm rule we can use. The logarithm of a power lets us bring the exponent out in the front. So applying that to both gives us y log of p plus 1 minus y multiplied by log of 1 minus p. And just like that, we've transformed a huge product of probabilities into a much simpler sum. And at this point you might be wondering, if we've already derived this expression, why isn't this our loss function? Well, remember what this expression actually represents. It's a likelihood. A larger value means our model thinks the data we've observed is more probable. So naturally we'd like to maximize it. But here's the thing. Almost every optimization algorithm in machine learning is designed to do the opposite. So instead of maximizing something, it minimizes it. So rather than asking, how can we make this likelihood as large as possible, we ask, how can we turn this into something that we can minimize instead? The simplest solution is to multiply these entire expression by -1. Now, if the likelihood increases, our loss decreases, and if the likelihood decreases, our loss increases. So in other words, minimizing this new function is exactly the same as maximizing the original likelihood. And that's why our loss function becomes that on the screen. This is what's known as a binary cross entropy loss. So before we move on, I want you lot to notice something. We never started by saying, today we're going to derive cross entropy. Instead, we started with a much simpler question. How can we measure how likely our data is according to our model? Every step after that followed naturally. And eventually this formula was the only place left to go. Now that we have a loss function, how do we actually minimize it? How do we find the values of theta that makes this loss as small as possible? Because at the moment, our model has no idea which direction to move. It doesn't know whether increasing a parameter will make things better or worse. So in the next episode, we'll answer that question by introducing one of the most important ideas in all of machine learning: gradient descent.